Hey folks, Dario here. Today I have a crazy confession to make. I'm actually not a software engineer. I am in fact, hold on, an electrical engineer. This is the ADXL 345 that we're going to use. We're going to skim this datasheet. Don't worry about it. I'll spend just a few seconds on it, but I'll highlight some critical things that you need to look for. Obviously, you want to look at the supply voltage range. Our Raspberry Pi can deliver either 5 or 3 volts, so we are good here. We also care about the communication protocol, so we are going to use serial peripheral interface, and in an upcoming video, I'll use I2C. It's about time to move on to the coding. You can find the code on GitHub. Please follow the link on the description. And here's the architecture, guys. We are going to have a Raspberry Pi running and connected to the accelerometers over SPI. And then we are going to use UDP broadcast to share the acceleration data with all the devices connected to the local network. And this is powerful because it means that the devices can use a UDP broadcast address that they agree on without having to constantly switch it as you change networks and stuff. Check this out. This is how the Raspberry Pi connects to all 3 accelerometers. Notice that each device uses 4 pins to communicate. We have MOSI, MISO, SCLK, and CS. And now let's break down each of this. So keep in mind that this terminology was invented before the woke culture. Yeah, these names are a little bit extreme. They are from a different era, so keep that in mind as I explain each of them. So MOSI means master out slaving, and this is the pin that the Raspberry Pi will use to send data to all these devices. And then MISO means mastering slave out, and this is how the slave devices communicate with the master. And then you have SCLK, which is the serial clock. That means that all devices have to be synchronized and use the same clock to communicate back and forth. And finally, you have CS. CS is chip select. And I'll show you in the code, but basically it means that the Raspberry Pi can select with which accelerometer to talk with, and it will silent the other accelerometers. The first thing we need to do is to initialize our SPI configuration. After SPI, you need to configure GPIO, so that's general purpose input and output. If you remember the diagram, we said that each accelerometer has a CS pin, and basically what you do is when you want to read from a particular accelerometer, you need to set CS to 0. Then you perform the read and then set it back to 1. So let's initialize GPIO then. There you go. So we are opening the first GPIO chip that we find on the system, and then look at the pins that I'm using. These pins correspond to the chip select pins that are in this diagram over here. So let me address the elephant in the room here. Why bothering doing this in Rust as opposed to C? At the end of the day, these are C libraries. Both the SPI library and the GPIO libraries are written in C, and there are bindings to Rust. So why bothering? Well, this abstraction gives me 2 things, 2 huge advantages: memory safety and type safety. And that does it for me. You do take, even when Rust is a zero abstraction cost language, meaning that you don't add too much overhead by using Rust, the reality is that you cannot beat C in terms of performance. It's just a fact. But I'm willing to pay a small, teeny tiny penalty just to get all this type safety. Next, we need to actually configure the accelerometers. So for that, I have a handy function that I'll break down after, but basically we just go through each of the accelerometers using a for loop, and then we verify that we can actually talk to the accelerometer by verifying that when we request the register 0, which corresponds to the accelerometer ID, we get I think it's an E5. Yes, we get E5. So we configure the device, then we ask like, hey, what's your ID? If we get something else than an E5, then it means that something went wrong, and we just print an error and exit immediately. There are all these registers that you need to write and read from to configure the device. So for example, here's how you control the data rate. You need to write to this register here. And if you want to read the acceleration, then you need to read from these registers. The next step is to configure the UDP socket that we'll use to broadcast the acceleration data. And the last step is we're just going to read the acceleration in a for loop. So what we do is we generate a payload that is a CSV row that contains information from all 3 accelerometers. And we just do that in a loop. I think we could remove this sleep, to be honest with you. Fantastic. Let's go ahead and start the client first. So cargo run release to turn on some optimization, and then the name of the binary is client. Let's do this. So here I'm printing. Every time I go through the ID check, I just printed that to make sure that I'm making progress. And now I know it's streaming. Now let's turn on the server. So cargo run release, and the name of the binary is server. We didn't look at that code yet, but that should be fine. I'll show you in a second. Release. It's running now, and let's see if we can find that juicy file with the rows there. And I think I see it. So if I tail the file that is generated, I see that yeah, we have data. We're online. Boom. So this is fantastic because now I can run this server process anywhere within my local network. And you know what? Let me do that. Let me bring my laptop. Cool. So I started the server process on my other laptop and check it out. Bam. It's wonderful. I really like these like distributed computing stuff over UDP broadcast. I think it's very powerful, and no wonder that we use it at May. And yeah, I know some other companies use it as well. But this is pretty neat. I'll give you a super speed run of how the server is put together. The big takeaway here is do yourself a favor and use Queen UDP. It's a fantastic crate, and they figure out some problems with the standard UDP sockets and socket 2 library. Create a nice crate for you to use. And yeah, so all the server does is here we are creating the CSV file that we're going to use. We name it based on the timestamp that we take when we start the process. Then we set up the UDP socket. There's some magic in there. Let me know in the comments if you want me to dive into it, because it's actually pretty tricky stuff. And then we create a loop and we just pull frames from the socket, parse them right here and write it to the file. Check this out, this other video where I built an RC car using Rust and a little bit of Python, but don't tell anyone.